Having looked at some simple matrix terminology in the previous slides, now we'll take a look at some simple operations we can do on matrices and vectors. And again, a reminder, please make good use of your ability to pause and rewind what you're looking at here, because I will be talking, there will be words on the screen. I may not be saying exactly the words on the screen, so you might want to be able to pause and hear words and also read words before you keep moving on. So in these slides here, we're going to take a look at addition and subtraction of matrices and vectors, and it's not a separate thing. I mean, vectors are matrices, so what we can do with one, we can do with the other. Scalar multiplication, which is different than just matrix multiplication, that's going to come later. Dot products of vectors, which most of you have seen before, and some of the information that we can get out of a dot product. So simple matrix algebra. Two matrices sitting side by side, are they equal? Well, it's pretty obvious when they are. They're equal when they have the same size and when each and every entry is the same between the two matrices. If you have two matrices of the same size, you can add them or subtract them simply by forming a third matrix of the same size as the originals and doing the operation entry by entry, adding up the first entries, the second entries, and so on. And we can do something called scalar multiplication to any matrix and or vector, which means just take every entry in that matrix and multiply it by the given scalar. So here we go. Here's an example. We're going to take the two matrices there and compute A minus 2B. So we will form the matrix 2B. So we're going to go through matrix B, multiply every entry by 2, and then do the entry-wise subtraction of A minus 2B. So there we set it up. A minus 2 times B. There we've completed doing 2 times B. The minus sign is still waiting on the outside, but every matrix or every entry in the second matrix is now doubled, and now we're just going to go through entry by entry and do the subtraction. So 1 minus negative 2 for the upper left, say 2 minus 8 for the lower right, and so on. And when you've done it for all the entries, there is your result. Make sure that you can go through and reproduce all those numbers and tell me about any mistakes that I've made. Another example, negative A plus 3B. So we're going to change the sign of all the entries in A. We're going to multiply all the entries in B by 3, and we're going to add the results. So there's A with a negative sign waiting out front. There's B with a 3 waiting out front. We do both of those operations, and then we add the results entry by entry. And there you have it. And again, remember, you only can add or subtract matrices that are the same sizes. Scalar multiplication you can do to any matrix or vector of any size. That's easy. Okay, dot product. Now this is a little different. Dot product is something that happens only on vectors, not necessarily on matrices. So here's two vectors that are laid out. Their components are listed just by number. The vectors are named u and v, and there's n entries in each. The dot product only works when the vectors are of the same size. And the way the dot product happens is you just go down the line and you multiply the first entries, the second entries, all the way down, and then add up all those little mini products that you just got. Here's an example. The first vector is 3, 4. The second vector is negative 1, 2. Their dot product, well, take the first entries and multiply them. Take the second entries and multiply them, and then add up what you get. Another example with bigger vectors, but it's the same idea. First entries, negative 1 times 5. Second entries, negative 1 times 2. Third entries, negative 1 times 3. Add up the result, and oh look, we got 0. And that's interesting because neither of those vectors has zeros in it, and yet their dot product became 0. Okay, so here's a couple of points to note. The dot product is a kind of multiplication that we can do with vectors. You're used to just regular old multiplication of numbers, like 5 times 4. When you do scalar multiplication, i.e. multiplication of just numbers or constants or variables, we sometimes write the product without even putting a product symbol, like AB, for the product of number A and number B. Now with vectors and the dot product, we need to put in the little dot symbol because there's another type of product down the line called the cross product, and you have to be able to tell which one of those you want to be doing. So you can't leave that symbol out when you're doing dot products of vectors. And as we noted, when you have two numbers and you multiply them together, or two algebraic expressions in general, you multiply them together. If you get 0, that meant one of the originals had to be 0. With vectors and their dot product, that's no longer the case. A dot product of 0 does not mean that one of the original vectors happened to have zeros all the way down the line. And then the other interesting property of dot products is you put in two vectors and out pops a single number. So you take two vectors and convert those vectors into a single scalar value, and it turns out that that value will have some interpretations. So here's something we'll see and then hold that thought, right? So if we want to calculate the length of a vector, you've probably done this before. We're going to use the magnitude notation, which is double vertical bars. It's like an absolute value on steroids, right? You're just going to go down the vector and take the first component and square it, take the second component and square it, and then add up all the little squares, and then take the square root of the whole thing. That's how we find the length of a vector. And you might have noticed before that in 2 dimensions or 3 dimensions, this is just the Pythagorean theorem in action. Now, looking at that expression, can you see a dot product hiding in there? If you can, that's great. If you can't, that's okay. Either way, hold that thought. Here's an ugly formula. This is a way the value of the dot product can be used to tell us the angle between two vectors, right? So this formula is telling us, hey, if you have two vectors u and v, find out what their dot product is. You'll have that number. Then find out what the length of u is, find out what the length of v is. You have two more numbers. Now you have three numbers in place. The only thing you don't know is cosine of theta, and if you can dig out what theta is, then you've discovered the angle between the two vectors. This leads to some interesting conclusions. One is that if you have two vectors that are orthogonal, that's the fancy way of saying perpendicular, right? We always like to make things sound fancier, so we sound smarter. If vectors are perpendicular, the angle between them is pi over 2. Look what happens. Cosine of pi over 2 is 0. Don't grab that calculator. You should know this value. And so if you have two vectors that are perpendicular, meaning that the angle between them is pi over 2, that's the meaning of perpendicular, their dot product is going to turn out to be 0. What happens if you take the dot product of a vector with itself? Well, the angle between a vector and itself is 0. It's the same vector, so there's an angle of 0 in between a vector and itself. Now there we know that the cosine of 0 is 1. Again, don't grab that calculator. You should know that value. So if we go back to that nasty formula and take two vectors that happen to be the same vector and tidy up our formula with what that means, we can actually solve that to discover the length of the vector. And the length of the vector gets written in terms of a dot product. And if you actually carry out that dot product of the vector with itself, and here we've come full circle to that slide a few slides ago, where I asked you to hold that thought, where we gave a formula for the length of a vector. So to remember the length of a vector, just remember, do the dot product of the vector with itself, take the square root. If you can remember that, you don't have to worry about anything worse. Here's an example. Let's test if the two vectors on the screen are perpendicular. Let's take their dot product. Oh, we got -6. Make sure you see how that dot product worked out. Since their dot product is non-zero, these vectors are not perpendicular. If they're not perpendicular, let's find the angle between them. Well, we already calculated their dot product, so we have that number to put in place. You can go off on the side and find out that the length of each of those happens to be square root of 13. Let's put those numbers in place and solve that for theta. Now, the inverse cosine of -6/13 is a gross number, so we're just going to say, hey, that's in its exact form. We're going to be happy and leave it like that. But whatever angle that is the angle between these vectors. Finally, let's find the length of this vector. Remember, to find the length of a vector, do the dot product of the vector with itself, take the square root. So the length of this vector is square root of 6. And there we go. In the next set of slides, we will look at matrix multiplication, which is a lot more fun than anything we just did here.